All right. So we've been talking about some of the recent projects and applications that we've developed, and I really wanted to show off some things that a couple of the guys here have done. So today we have Philip Babb and Nick Vitello, actually our two newest employees here in Industrial Insight. They're going to show off some things that they did at a power plant recently that I think super neat. And I think also, just like I did with the spare pump application, I think this has applications in multiple areas. So just to set this up, this customer had gone to a gas powered power plant, and they had been a coal fired power plant for a number of years. They had also reduced their workforce from, say, 140 people down to 30 or 40. So big reduction in force. They're not running all the time. They're not base loaded anymore. And it became very, very important for them to be able to start up on time and in the allotted time that they had given the grid operator, because it would cost them a lot of money if it didn't start up on time. So I challenged Nick and Philip to build some useful things for the site, and I'm really super proud of these guys and what they've done. And so I just wanted them to kind of walk through it. So what we're going to do is we're going to start out with Nick showing a startup screen and set of start comparison screens, and then Philip's going to show the next step of what we potentially could be doing, and he's actually going to show you some multivariate analysis that he's been playing around with, trying to find some patterns in some of the startups. So I won't steal his thunder. So Nick, why don't you lead us off?
All right. Yeah. So, yeah, Philip and I both worked on the AF, and we've created the AF structure, building out Pi. And I focused a lot of time into monitoring the startup process by capturing event frames and building out the associated dashboards and graphics to represent the startup window. This first graphic, the intention is it to be viewed during startup. So these values are all critical to the startup process. They are some of the most important points, and they dynamically update during the startup window, so operators can quickly check where they're at, read some of the most critical readings in real time. You'll see they're broken down into different types of temperature, pressure, flow, and more recently added, this is a steam table, which represents the degrees over saturation. And as you enter through or move through the startup window, you can see all the values dynamically updating. In this middle section, this is kind of interesting because this is where the event frames come into play. In the event frame, we capture the start, which is triggered by when the air heaters kick on, and the end is when the unit achieves ADS, which is basically turnover to the utility company for operation. You can see here we created an estimated time to ADS. This uses historical averages along with the preheat curve, which was imported into AF. Using all those in analytics, we were able to create a reasonably accurate estimated time to ADS. Below here are some of the event frame points, and they're just various stages throughout the startup process. The dashboard also displays alarms when certain values are out of range to let the operator know they need to start taking a look at potential failures in the startup window. And yeah.
So real quick, do you want to talk about where those curves actually came from? Because I remember seeing those.
The curve for the preheat for both Unit 1 and Unit 2 came in a PDF
It was just
drawing,
it was
which was
scanned in
likely,
from a book, right?
yeah, it was probably a picture
Right.
scan.
Right.
And
Rotated at 15 degrees.
Yep.
yeah, we cleaned up the image, we managed to plot it out, and added those points using an AF table.
And I thought that was kind of interesting because we've done some things in the past where we've used some software to try to estimate what that curve would look like, what the actual functions are. I don't even think you could do that here. It wasn't even good enough. I think you guys had to do some manual work this time, right?
Yeah, we had to clean
Yep.
it up a little bit before we could really plot out the values. Yeah.
So that's kind of an often overlooked, thing that we sometimes have to do. Is the information isn't always super clean. So okay, continue.
Okay. But yeah, that's the intention of this graphic. It's during startup, something every operator would want to look at and get as much information as they can about the most critical points all at once. The next is the startup review. So this is for reviewing these startup event windows after they occur. You can see here you have a large startup window graph with a few preset points, attributes already dropped in, including the first stage shell temperature and the different phases of the startup window, one of them being what's called the fired state, another being when the tiebreakers close, and finally at the end of the window when they achieve AES, signifying that startup event is over. Over here are some of the properties and different times for how long it took to get to some of these events, the overall startup time. They also indicate what type of startup it is. And there's 3 different types of startups: cold, intermediate, and hot. And based on the shell temperature, this significantly affects the overall startup time. Down here, you'll see these are all the actual event frames, the startup windows, and you can see different startups and apply the time range. The chart is automatically going to go into that time range. That's the purpose of this, to be able to...
So who's the target audience for this one? Who do you anticipate using this screen? Just an engineering tool, operations management? Who do you think?
For me personally, I believe this would be for managers and engineers to be able to review the startup windows and be able to take a look at what's affecting the startup time the most.
Right. So the first graphic was really targeted more at the operator, right? This one's really more targeted at someone who's looking at more long-term, potential benefits, right? So.
Yeah, exactly.
Okay. And I see you've switched to Unit 2, so you can switch back and forth between Unit 1 and Unit 2. This plant has 2 different units, so, yep.
Yep, seamlessly switch between assets.
Yep.
Just by dragging and dropping and reapplying the time range.
Excellent.
Yep, and the third is the event comparison, and this is a native PyVision screen that's been a little customized to basically stack these startup event frames on top of each other from 0 hour to the end of the startup, whatever that duration that may be. So using this, you're able to really dive in to what's different between startups, and you're able to really compare and contrast startups that may be similar or very different. For example, this is the longest cold start out of all of them, and you can see with just the 2 points, the preset points, the unit had a trip during startup, which is why it took so long. So you can also add notes to these events, so operators can write in, or management can write in different reasons or explanations for why some startups may be longer or shorter. They can call out why some startups maybe were significantly faster than other ones. But yeah, it gets really useful when you start filtering out some of the more anomalous events and narrow it down to a tight window of relatively close startups with all the same shell temperature. And you start to see variations for when, example, the generators were starting to heat. This 2-hour difference right here, there's some cases where there's a 2-hour difference. This helps you point that out. That's a significant amount of time in a startup window. So being able to explain why that's happening is really important.
I think as a manager, I would look at this and say, okay, why did we not start at the same point? What else was going on, right? And in light of some of the other projects we've done, I'm almost thinking, down the road, you could even do an event list, do some kind of an acknowledgement or reason code button. Hey, this was a good startup. This wasn't a good one. Put in a reason code like, hey, we had a unit trip on this one. Maybe, and then as you said, put in the comments, and I could think down the road, as we get more data here, it could be pretty useful to even analyze that, say, in Power BI or something along those lines. It'd be pretty interesting anyway. That's powerful, but it's also inherently weak in that you have to compare things one at a time. What if there's like 150, 200 things you need to compare, right? What happens? What do you do next, right? And Philip, I think that's where you come in, right? So what do you say?
Yeah. Yeah. So, after spending a considerable amount of time in the customer system and getting to know their process, we started to look at some of this data that we're collecting from the event frames that Nick is just showing. So SIMCA is a software that we have a license agreement for, which is a multivariate analysis tool. So it essentially allows you to compare a large number of variables to one another. And I think the starting point is it's not the next step as it is another tool in our toolbox, right, where we still need to rely on the data that we collect from the Pi system, the information that we glean from their operations there, and kind of go back and forth. So maybe conclusions or ideas that we get from a software like this, we go back to the startup plots, right? And we try and see if we can pick out operational things that make sense to us or the customer.
Yeah, and I think you hit something really important, because a lot of companies out there are selling these machine learning tools. When, let's face it, SIMCA is a machine learning tool. PCA and PLS are machine learning or algorithms that are typically used in machine learning solutions. They're two of the mathematical tools that are used, but they're not a be all end all, right? They
Right.
tell you things, they give you correlations, but that doesn't always mean causation, right? And I think that was some of the things that you found in this too, right? So it kind of hammered home to you like, hey, this is a great tool, but we still have to have expertise, right?
Yeah, absolutely. I mean, it's really easy to, we can see some examples of that, it would be really easy to make conclusions based on what this shows you, right? But you got to be sure that the data is telling you what you think it is,
Yep.
right?
Yep.
And that's true for anything, really.
Yep.
But so yeah, we start out here with some of the event frames that Nick was just showing. In this particular case, we have one of their units, all of their cold startups for one of the gas units over 5-minute intervals, and we're just grabbing pretty much any variable that we think might affect. You probably can't see what these variable names are, but you can at least see that there's a lot of them. And we're trying to see if there's any correlation between any of these variables to one another. Are there any kind of hidden relationships? Because realistically, right here we have 165 columns of unique variables. There's no way we'd ever be able to compare all of those to one another and make any meaningful conclusions, right? The most we can really, as humans, understand is maybe 2 or 3 on a plot, and you start to pick out patterns, but it becomes very difficult after that. So that's really kind of the power of the PCA analysis, is it allows you to pull in large sets of variables and compare them to one another. And so once we make our PCA model, and there's been some stuff that happened before this, we filter out some of the outliers, we filter out things that don't make any sense, or, sensor noise that we know isn't really representative of what's happening in the process. Or, something trips, stuff like that. We take that out of the model because we want this to tell us, the overall process that they tend to follow and the relationship between each one of those variables during that process. And so what we're looking at here is, right now these are colored by start time, but let me change this to date.
And while you're doing that, one of the things I want to just kind of explain in that scatter plot there on the top left, is every one of those dots represents one row of 5 minutes in time, right?
Yeah.
So the idea is this is actually a 3D plot, really, that being shown in a 2-dimensional space, right? So what it's doing is if the variables are essentially the same, from row to row, those two dots will be very, very close together. If the data is very different between those two rows, they will separate. And so what we're kind of looking for here is, are there tightly clustered things, or are there things that kind of move and change and do things that kind of help us to figure out what's the story and what's really going on here? And I think that plays into kind of what you found here. So,
Yep. Yeah, that would have been a good thing to explain. And so yeah, and that's kind of the general idea behind the PCA, right? Is each one of these points, I can just highlight one of these startups, but each one of those points along that startup is exactly like you said, one row of that data. And you can see that, for each one of these startups, they follow a general pattern, right? Which is good. We can at least say that our model is valid. It's picking up this process pretty well. And so then we start to look at, okay, well, what is the same and what's different, right? So the first thing that pops out to me is this region here looks really similar. So across all of the startups, regardless of the startup time, this seems to, track each other pretty well. And if we zoom in, I'm just, pardon me, we might edit this part out, but I should have prepared this a little bit. We can pull up one of our process variables to kind of help explain what's happening during this stage of the data. And the cool thing about SIMCA is you can highlight a section of this data, and it'll, on all of your plots, it'll highlight those points. And so there's a lot of like really powerful plots that you can pull up together and highlight and compare things to one another. And it's really, really easy and intuitive to do. That's one of the reasons why I like this software so much, to be honest.
Yeah, and
it's just easy to use in that regard.
And here you're kind of looking at the very beginning of the startup. So kind of what I think you had concluded here, and correct me if I'm wrong, is that generally when they're first beginning the startup, they're generally doing things fairly similarly. Generally.
Yep.
Right? Once we took out some of the burner firing rates and like which burners they were firing, because that didn't really seem to matter. But once we kind of eliminated that, everything's pretty much the same. Then it's when it kind of separates a lot.
Yep.
And that's kind of what this is showing right here.
Right. This is the turbine metal temperature. So, that's kind of the goal when they're starting up, is to heat up the turbine, right? So each one of these humps is one of the startups, right? And so this first section, you can see highlighted this first part of each startup, which is before that temperature starts to increase, which tells us that this is when they're getting their boiler ready to release steam to the turbine to actually heat the turbine up. And so all of those initial procedures that they go and follow, like starting their burners, their igniters, right, their air heaters, and any other equipment that they need to get going, their steam drum, filling that up, building pressure in the boiler, superheating the steam, all of that stuff is before they've begin to heat up the turbine. And from what it looks like on here, that's all pretty similar.
Yeah. And I noticed,
which is good.
And I noticed you had done something, looks like maybe with the temperatures, because that's really low for the temperatures. You did some normalization here, didn't you? If I remember.
Yep. So all of these temperatures in this data set actually are normalized by the ambient air temperature outside. So, we noticed that this first startup is in June, and then this last one over here is December. And before we normalize it, you can see this trend. It's going down in temperature, right? And that would give you conclusions. It would say, well, the December startup was a lot colder than the June startup, and you're like, well,
duh.
It was cold outside.
Right.
So,
that's why they were needed. Yep.
Exactly. And so that's actually a really good example of paying attention to trends that it gives you, because you might see a pattern and think, wow, here's my answer. Like, this startup is slower than the other one because look at these temperatures, they're so much lower. And it's like, okay, but this is December and that's June. And so you have to think about stuff like that. And it's a very iterative process, right? You start somewhere and then you work through the outliers and any sort of normalization that you need to do, adding variables, taking out variables. Yeah. And then of course, talking with
so wait,
customer.
let me get something straight. So basically, you just don't throw a bunch of data at a data model and whiz bang, there's your answer. That's not how it works.
I wish.
Yeah.
I mean, you know.
But that's how some people sell this, or they have sold
Mm-hmm.
it in the past. And the reality is, you're highlighting, and you're so relatively new to this kind of analysis, and you've already realized, you know what, it's not a magic bullet. It's incredibly powerful, but it's not a magic bullet.
Right.
It helps you to kind of hone in on things, but there's still that back and forth with the people who actually know the process well, right? So I think it's really good for you to point that out. I think that's excellent. So
Yeah, I mean, junk in, junk out. I think it's you got to be really careful about kind of what conclusions you're making. Um, so yeah, then we move on to past after this inflection point, and I guess I should have pointed out to begin with. I mean, we kind of said it a little bit, but this first part corresponded to the first part of the startups, and you could probably guess that this second part is the rest of it. And so why is this data so spread out, right? That's the next question that we're going to ask is, well, this looks great over here, but then they open their steam valve and they start heating the turbine and everything separates. And so, that kind of becomes the focus of the analysis, right? Like maybe there's something operationally happening in here that they could hone in on and try and tighten that up, right? So we can also color this by different classes. Right now I have my class ID set as the date of which the startup occurred, just because that's how we're used to seeing it in Pi, but we can also put things like the total time that it took them to start up. So, we have our 19-hour startup up here, and then we have a 26-hour startup down here. And those are two, opposite ends of the spectrum, right? One's really fast, one's really long. And we can actually compare those to each other. And that's another really powerful thing about SIMCA is it's really easy to compare all of the contributing variables into the differentiation between how SIMCA sees each one of these in the model. So in this particular example, it thinks that the hot well temperature and feed water temperature and this duct temperature, what's this over here, the other air duct temperature, are the main drivers in the difference between these two data streams, essentially. Now, I happen to know that this 26-hour startup there's a trip that's been filtered out, the actual trip itself, but it's kind of artificially long. So we can even compare that to something else where we don't exactly know what happened, right? We just know that it took longer. And I think I did that one backwards, so it's on the other side. But so this turbine oil from coolers, which is seems to like pop up quite a bit. Again, these temperatures are all been normalized, but you see here, even back in June, this is the June startup. It took 23 hours, and then we're comparing it to the fastest startup, which was 19 hours in December. So opposite ends of the spectrum in terms of time, as well as ambient air temperature outside. Again, we've normalized by temperature, but still we see a really low relative temperature here in the June startup versus the December startup. And, come to find out, you go to the customer and you ask them these questions. You say, well, this is what we're seeing. Does this make any sense, right? Because, at the beginning of this, you said, we're not experts in power plants. We learn what we can, and we learn quite a bit. But yeah, at the end of the day, we're not experts in it. So, but it turns out that this particular measurement, this oil, along with the bearing temperatures, are largely responsible for, or I should say, can cause significant delays in the turbine getting up to speed, if I remember correctly. So if these temperatures are too high or too low, then they're not able to roll the turbine up. So this is a holding point for them, this variable, assuming it's out of some range. And so that's just kind of a little bit of what we're kind of doing with the software, right, is we get it to a point here where we start asking these types of questions, you know, try to pinpoint whether or not that makes sense from an operational standpoint. So here you can see all the bearing temperatures. These are all fairly large differences, and so like again, yeah, this bearing temperature is really low for June. So it probably took them a long time to get within an acceptable range to fire up the turbine. So
Well, and I think what you've done and what you got the customer really thinking about is, and I think here we found there's not enough data, there's not enough startups for them to really come to any meaningful conclusions. There's definitely some interesting things like that turbine oil cooler, is something that may end up on a screen somewhere like, hey, that's a key KPI we've got to nail, right? But I think what, this particular group said was, hey, this, we don't have enough startups to really make use of this, but this is incredibly powerful. We didn't even know this was possible, one.
Right.
And then two, we showed it to their sister plant, who is a coal plant. And I think, well, we've got a lot of problems that this could potentially help us solve. We just got to go figure out like where you can help us first. Right. And so I think it opens up a different world and a different mindset of what people are thinking about. I know it did for me because I had someone that kept telling me about, a software tool like this and, hey, you can do some really powerful analysis very quickly that you can't do by just doing things in Pi and just comparing one thing at a time. So I think I think this customer realized that very quickly. So, and I think you guys did an awesome job with this. I really do. I definitely, like you said, we can't be experts in knowing how a power plant runs, but given that, I guess it was September, you had never seen a power plant before. And Nick, I guess you you probably started work on this project 1st of December. Yeah. So, I mean, you think about what you guys were able to come up with in such a short time, it was pretty neat, I thought. And I wanted to highlight it. I wanted to brag on you a little bit. So I try not to do too much bragging on stuff in YouTube and too much selling. I'm trying to more educate. But I wanted to brag on you guys a little bit. I thought this was really handy and really good. So,
yeah.
Yep.
Well, I really enjoyed the project. I learned a lot because, while I do have a background in Pi, it's never been on the industrial side.
Right.
So this has been, I really, really enjoyed the project.
Yeah.
Yeah.